My name is Diana Sampson, and with my colleagues from the Coordination and Support Action of the European Quantum Flagship, the QFLAG project, we prepared this webinar to illustrate by some concrete examples how quantum technologies might impact our lives. Our applications and market team, led by Philippe Chomaz, who will moderate the roundtable discussion today, will work on identifying new and future use cases to disseminate and bring them to the market, both in high performance and mass market applications. To do so, we intend to organize several workshops to bring together developers and users of quantum technologies. Due to COVID-19 crisis, we were obliged to cancel our workshop planned this year at the Mobile World Congress in Barcelona, but as we seek inputs from market and users, we hope to set it up next year and see you there, place and date to be confirmed. Thus, this year we carried out 3 workshops remotely with think tank experts to collect and discuss use cases from different domains and give you a global picture of the ecosystem and the market impact of these use cases. Results of these brainstorming sessions have been documented in a public report, and some of the experts from the think tank are here today to give you an overview of a possible use case. Before handing over to Thomas, who will introduce you to the content of the session, I want to point out that we also regularly conduct surveys on qt.eu website on intellectual property, skills, and education, which are closely linked to our use cases developments. And actually, you can participate to the ongoing Delphi survey addressing skills and education. So I invite you to follow us on the qt.eu news webpage or to register directly on the directory on our website with a QR code that you can see on the screen, which is shared throughout this session on speaker's presentation. So I will hand over to Thomas, who will introduce you to the content of the session. Thomas.
Hello, good afternoon. Diana, could you go please to the next slide?
Yeah. So.
And one slide more, please.
Yeah, so this is the QFLAG team, and here the content of the session. Yeah.
So here you see the agenda. So we are at 12:03 now during welcome introduction. And in 2 minutes, we will start our use cases, which will be presented in talks by 8 different experts. So we will start with quantum communication with Hannes Hübel, Paolo Villoresi, George Canelos. Then we will go to quantum computing, Peter Liemacher, Marc Bourgeron, Frank Wilhelm Mauch. And we will end around with quantum sensing and metrology with Frank Deppe and Florian Schreck. At 12:40, then we will go into a roundtable discussion, which will be moderated by Philippe Chomaz. So I would like to remind you, or I would like to inform you that there will be no question and answers sessions after the individual presentation. So if you have questions or comments, please put those into the chat. And we will pick up these questions then in the roundtable discussion. So I would like to start now with the use cases round. The first talk is by Hannes Hübel from the Austrian Institute of Technology. He's also coordinator of OpenQKD and UNIQORN. Hannes, please go ahead.
Johannes, you are
Hello?
mute.
Mute.
Thank you. Okay.
Is it working now? Okay.
It's working.
Sorry about that. Okay. Hello, everybody. To my use case presentation on how to secure medical data using quantum key distribution. Okay, I think everybody has experienced first hands-on that if you go to a doctor now or to a hospital, your medical data will be saved as in a digital format, everything from patient's records to your diagnosis. So I think it's really important to make sure that this data is safely stored at some database. What's the problem with this storage? The issue is it needs to be a long time storage because even your biometric data or medical data is still valuable after 20 or even 30 years time. So that means we really need forward security, meaning that whatever we save now is secure even in many years. And this is an issue because, as we will hear later, quantum computing has made tremendous advancements in the last years, and we can not longer assume that the current crypto technologies are secure in the future when a quantum computer comes online. So what can we do about it now? Well, first of all, if you look at the picture here, we can first try to save or to secure the data at rest. And we can do that by basically splitting it into more than one location, into more than one share. So this is called secret sharing, where you basically split up the data, you distribute it to different centers, and then even if someone cracks into one storage location, they cannot gain access to the data. They basically need more than one share in order to recover the full information. So this was the data at rest. What can be done for the data in transit? Here we can use a quantum technology called quantum key distribution. We basically encode a random string on photons. We basically transmit those photons from a sender to a receiver. This can be done in optical fiber or using a satellite link. We can then decode those photons and end up with a symmetric key between the sender and receiver. And this symmetric key is then used to classically encrypt our message from the hospital to the data center, for example. And since the security is based on quantum physical laws, rather than just complex computation, this key exchange is information theoretical secure. That means whatever power an adversary has, so even if the adversary has a quantum computer, it cannot crack this key exchange and the encryption. So together with secret key sharing, we can really secure the data, medical data, biometric data, being transferred from a hospital to a data center and stored there for a long time. Now, this is a use case which will actually be deployed in reality as part of the OpenQKD project. So we work together with a hospital in Graz, which is in southern Austria. We have a local network company as well, which basically provides the data centers. So we're really working with end users together in a real environment to demonstrate this use case. And as you can see, we also have infrastructure provider and device providers for QKD, for the classical encryption, and for the secret sharing. And this also shows the value chain. So the different components, the different levels you basically need in order to have this use case in a real world environment. In addition, we also need experts from both classical and quantum cryptography, because as I've shown before, this use case is really based on a complementary approach between quantum and classical cryptography. And finally, we also need people responsible for network design and deployment. So if you want to basically know more about other QKD use cases, please follow our website, openqkd.eu, where in this project we have up to 30 use cases all scattered around Europe, and we will demonstrate them live in the field over the next 2 years. So if you want to basically see where a use case is happening near you, please go to the website and have a look. Thank you very much.
Thank you very much, Hannes. So our next speaker is Paolo Villoresi from the University of Padova.
Good morning, everyone.
I would like to thank Hannes for having introduced this subject that is very relevant also for my case. Do I see my slides? These are coming, I presume, in a moment. I see them here. Yes. There we are. So, well, we all know that from space we are getting a lot of data in the sense that for navigation in the car, for, so you know, it's not this. Okay, the next one. Yes, thank you. Navigation in the car, monitoring risks on ground, expanding the coverage of telecommunication network. Well, we all know that data is really expanding in terms of technology and, of course, also in economy. So the point is that this has to be taken very seriously at the continental scale. Besides the economy that is generated by using the data and the space as a means of communication, also the manufacturing of satellite is indeed very interesting. As a note, the overall worldwide relevance in terms of economies of the order of 250 giga euro worldwide, 70% on manufacturing and the rest for launches. Okay, so as it attracts more interest, space terminals and space economy, space application in general also calls for stronger protection. Very much in line with the case of Hannes about medical data. Example of practical issue to protect are the secure download of images, okay, that we know that are relevant for taking decision, of course, related to evolving events, okay, or on environmental cases. Control command of spacecraft that can be strategic, and also data relay over intercontinental links. Okay, so please the next. So the satellite indeed may act as a distributor of keys that can then be used for all these different cases. So it may fly over different ground stations, and you shall have a key that is exchanged between a satellite and a station A, B, C, D all over the world. And then the satellite, the operator, decide to create pairs of simply say the standard bitwise parity of these two keys that allow the two stations to distill a secure private key between themselves, regardless on the separation on ground. So it's something that will cover worldwide the secure communication protocol. So this is something that has seen the light in Europe, definitely, with many early developments of these, starting from the feasibility demonstration of the photon exchange, then feasibility study on this that started about 20 years ago, okay, in Europe by ESA, by Italian Space Agency as well. And then there were demonstration on ground on the say the link in horizontal direction, beside, of course, the fiber developments that they took part in parallel. But demonstration across, for instance, the Canary Islands and many other locations, just to study what is like to address a free space channel of a long length. And from 2008 on, there have been demonstration on quantum communication, essentially using retroreflector and existing satellites. And this has reached a very high orbit like the GNSS satellites. These works, these researches, has actually spurred, sorry, this, okay, yeah, a European plane that European Space Agency is coordinating within the telecom domain, essentially, aiming to develop all the tools that are needed in space to create first a demonstration, then a constellation that will actually provide and address these cases with satellite using as much as possible all European, say, product technology, know-how, patents, and things like that. This is, of course, a space counterpart of the ground initiatives that leverage very much on the OpenQKD project test demonstration, and as actually a point of contact in the case of our node, which we are dealing with the intermodal communication between free space link and fiber links. Okay, the European community has also devised a roadmap for developing these technologies in Europe, starting from indeed the low orbit demonstration of the so-called prepare and measure protocols, moving on in the, of course, evolution of the source technology, the rate, also the type of protocol that may also embrace the entangled version that make no use of this trusted node thing, and also is very instrumental for a crucial issue that is the distribution of entangled state, that is the so-called quantum internet over global scale. Just to tell you, one piece of novelty is the daylight QKD, which is something new because usually the demonstration being done only at night. That was allowed by the combination of integrated optics, changing detector technology in the source technology, and this is something that the Italian Space Agency is going to launch and demonstrate in space. It is indeed an opportunity for Europe in the sense that it is definitely stimulating the synergy of various branches of technology, integrated photonics, microelectronics, sensing. This will spur the development of ideas from the labs to spin off and the larger and larger industries, European industries, and the potential user actually are very broad. Like Hannes has mentioned, from governative to private and public services. This actually is calling for the skill of the quantum engineer that has a role that is, of course, to be formed by the university, but then brought to the market and brought to industries and fostering new positioning high-tech job market in Europe. Also, the intellectual property is something very delicate and very important to underline that essentially will provide, say, a solid ground for the essentially advancing in Europe for this domain of the quantum communication in space. So with this, thank you for your attention. And space is indeed a very intriguing subject. No limits, but horizons. The more you rise, the more you see. Thank you.
Thank you, Paolo. We are already a little bit our schedule, so we have to hurry up. The next speaker is George Canelos. Please go ahead.
Hello, everyone. Can I have the lead? Oops. So, good morning, everyone. My name is George Canelos. I'm affiliated with Smart Internet Lab and the High Performance Network Group from the University of Bristol, which is in fact a leading team worldwide on classical networking. And we aim to bring this expertise also on the quantum realm in order to implement a dynamic quantum network with intelligent entanglement distribution. So within the UNIQORN project, we have been working with photonic integrated quantum devices in application, of course, such as quantum security and quantum key distribution for 5G, for example, but also beyond quantum key distribution in developing novel applications such as computing applications such as one-time programs. And I'm going to be discussing this a bit later in my slides. More importantly, we have identified entanglement distribution as an excellent tool in order to simultaneously distribute multiple quantum states across a network. And very recently, there was a demonstration with 8 users on a field trial that attracted a lot of interest. Of course, it was a static network development, but it managed to attract a lot of interest and in fact got to the coverage of the Nature magazine. Even more recently, within UNIQORN, our partner AIT demonstrated a step further and allowed for entanglement distribution to be dynamically reallocated by using active optical switches. But the main question now is how do we scale these quantum networks beyond single-digit nodes of a lab experiment? And this is where the expertise from the classical networks comes. And if we follow the examples, there are two things that we mainly need to implement. First, we need to establish a flexible and dynamic quantum network deployment that will allow for reconfigurability of the network topologies. And then we need some sort of centralized and intelligent control, such as, for example, the software-defined networking paradigm in classical networks that will allow for overviewing and monitoring the whole of the network, and thus making decisions towards optimizing the resource usage and allocation, or optimizing the performance of the quantum links versus the application and the service requirements. So within UNIQORN, we are working in three distinct layers towards this goal of intelligent entanglement distribution, with the network layer implementing a quantum-aware software-defined networking controller by developing advanced, if you like, algorithms on optimizing the network planning and operating or driving the quantum devices, the novel quantum photonic devices that we also aim to integrate, such as the time-bin entangled source that is driving a photonic integrated quantum reconfigurable add-drop multiplexer that was actually just released from our project partners. And we aim to apply this over our field testbed around the city of Bristol in order to demonstrate potential applications such as quantum key distribution or one-time programs. And at this point, please allow me to describe briefly what one-time programs are. So our partner from University of Vienna has been developing that, and the aim is to have two users. So Alice wants to share a classical program with Bob, but Alice wants to do it only once and without giving the full logic of the program to Bob, while Bob wants to run this program, but without revealing his own inputs. So, in fact, the University of Vienna has recently managed to demonstrate this by integrating or transmitting the truth table of the program, encoding it into the quantum states and transmitting it through an entangled quantum channel to Bob. And Bob used his own basis measurement as the input to the program in order to execute it, of course, in a probabilistic way. Potential applications for that are software licensing, double spending protection, delegation of one-time signatures, etc. There are more than that. And if we look across the value chain for this entanglement distribution network, we see that we need expertise such as software developers for the protocols and for the interfaces to be developed, as well as quantum device expert, and apparently work on the application and the end user side. So if you like our work and you want to follow it, please link with us within the UNIQORN project. Thank you very much.
Thank you very much, George. So now we leave the quantum communication topic and come to quantum computing. And our first speaker is Peter Lehmacher, who is part of the security research team at SAP in Karlsruhe. Go ahead, please.
Yeah, thank you. If you could just advance one more slide, then perfectly. Yeah. So, of course, as a software company also dealing with the cloud, we have many use cases being located in quantum communication, but also in quantum computing. What I will talk to you today is just one particular use case from some of our customers, and that's located here in the field of chemistry or physics, material science. And so I just want to guide you through it quickly. So what's a typical problem there? It is that you usually want to have some predictions of a material or of a chemical compound, of some drug or so. You want to know certain properties without even going to the laboratory and synthesizing it and measuring it. You really want to start in the beginning and do a calculation, which is of course much quicker than just synthesizing it first, because this of course all costs money. So what you actually do is you do incorporate calculations in order to make these calculations faster. And so there is existing programs in the classical world. On a classical computer, you can do that. You can calculate these properties, but often it is like that when it becomes interesting, and those molecules you do want to describe, or these materials with interesting properties like batteries or so with high storage, often exactly in these cases, the classical calculations do fail, and you have a problem actually in accurately describing it. And this is exactly where quantum computers come in now. They have algorithms which are much let's say more robust, they're much more accurate because of their very nature. Of course, you're also solving a problem related to quantum effects, so it's this kind of natural also to use quantum computers for this. One particular algorithm that I outlined here is this variational quantum eigensolver. And this has the property that it actually finds a solution and it finds it robustly. So it means that the number that you obtain there, actually you can trust, which is the difference to the conventional calculations you do. They have a lot of approximations, and sometimes the number they return to you is a good one, but sometimes they're really off and you cannot trust it. And so that's exactly why you would also have some kind of benchmark. So yeah, you can, if you want to be sure, if you can trust your calculation that you do classically, you also would do let's say a benchmark calculation also with this variational quantum eigensolver, and then you can compare the two numbers and be sure that you can trust the other number as well. The way this would work is, of course, also it will be a hybrid algorithm. So that means it is not a quantum computer only. So this quantum computer will actually be controlled by a classical digital computer, which sort of formulates the problem and then gives a sub-problem of a task basically to the quantum computer. The quantum computer would calculate then its task and send the result back to the classical computer, which itself would generate a new iteration of it and then send the problem back, and so on and so forth. So the calculation is hopping back and forth between the classical and the quantum computer. And then the last point, actually, yeah, like who will benefit from this quantum computing approach? And of course, as I already alluded to it, it would be companies that do such pre-screening. You can imagine that you save huge costs if you have, let's say, 100,000 potential drug candidates, and you don't know which one is the most useful. Actually, you don't want to send hordes of scientists and researchers to the lab and synthesize all of them. You really would want to do a quick pre-screening, do a calculation, and make kind of a short list, maybe just the 20 most promising candidates, and then you would only do synthesizing them because you've evaluated before with your computational model already which are the most promising ones. And the kind of job opportunity that this creates is actually, well, one side also on the software side, but it's also very important to actually have some algorithmic development here for quantum algorithms, which is by no means trivial. So this is definitely a new skill set that is going to be needed and where we need many experts in the future. And with that, I'm handing back.
Thank you very much, Peter. Our next speaker is Marc Pocheron from Électricité de France.
Hi, good morning, everybody. Can you hear me?
Yes, we can hear you.
Thank you very much.
Switch on your camera.
Yeah. I think that, well, the channel has to move my, thank you very much. And you will have to click to at some moments. Well, on this picture, we see, sorry, as this picture, we see the different domain. If you can click, yes, thank you very much. We see the different areas of quantum computing we are currently investigating at EDF in the division of EDF. Just the next click to explain that the point is that many problems appearing in this domain which are connected to our activities in energy supply. Many of these problems do not have efficient classical algorithm to solve them beyond small instances, even on the most powerful HPC high-performance computing means. And the next click, sorry for that. Okay, a typical example, I will go on that later, is, for example, large-sized combinatorial discrete optimization problems in the field of smart charging of electrical vehicles. And more generally, all these difficult combinatorial discrete optimization problems appearing in all these areas are very significant for us and very important to solve. And next click, thanks. And we seek for quantum advantages on these problems, both in terms of calculus performances, that is solving more precisely bigger problems, and hopefully on energy consumptions. Okay, so next slide. Okay, so we are going to focus a little on a smart charging of electrical vehicle, which is a very important use case for EDF at the moment. So we are in a framework of vehicle to grid. So in this framework, we don't consider battery of vehicle only as demand for the grid to be charged, but also as resources for the grid. And so as a driver, you want to plug in your car to any charger, you want to charge your battery, of course, but perhaps you want also to make some money by contributing to the regulation of the grid, or to save costs, for example, by providing some power to some building or to your own house. And of course, you want to be ready to drive when you want with your own constraints as a user. So this is the global vehicle to grid framework, which will be very important for the thriving of electric mobility in the future years in France and in Europe. And you can imagine that we have many difficult optimization problems around this framework. We have to decide when do we have to optimally charge the different vehicles, and for example, how many load stations do we need in order to perform loads in an optimal manner. So we are focusing on two problems of this kind as a use case for our partners at the moment. The first one is a minimization of the total completion time of a set of electric vehicle charges with priorities. And the second one is the minimization of the number of stations we need to perform loads without overlapping under some constraints. For example, at most one electric vehicle per group scheduled on the same station. And the important point is that we are modeling these problems as general graph theory problems for which we have some quantum computing approaches available. For the first one, for example, we have the quantum approximate optimization algorithm, QAOA, which is available to tackle this kind of graph theory problem, which appears as a partition, an optimal cut on some graphs that we built from the instances of the problem. And on the second problem, we have also a manner to model it as a coloring, minimal coloring or maximal independent set problem in a optical graph, depending on the instances. Both of these problems are known to be very hard to solve on conventional computing. And we use QAOA and a quantum mathematical algorithm on readable atom Harris-based machines for the second one. Thank you. For the next slide, the last slide. Yeah, some clicks and it's okay. Okay, this work is conducted in collaboration with many partners, academic, industrial, and startups partners. Okay, so just to conclude on the subject, we can have a strong market impact because this kind of problem could upgrade capabilities of electricity mobility. Societal impact too, because it is important for public health. Electric mobility is important for that, for reduction of greenhouse gas and fine particles emissions. Significant impact on value chains, because all the development chain will involve many actors, end users, large companies, because we have to enforce a global constraint on the grid, academic and industrial research labs, and startups. And we have strong skills required for these problems, both in quantum computation and simulation and optimization, scheduling, and progression research. Okay, and to conclude, we can say that intellectual property requirements should not limit the collaboration with other partners in the current early phase of research and development on the topic. Thank you very much.
Thank you very much, Mark. Our next speaker is Frank Wilhelm Mauch, actually from Forschungszentrum Jülich, and he's also project coordinator of Open SuperQ. Frank, go ahead, please.
So yes, thank you. So I'm rounding this off by talking about basic research, which, if you want, is the most wide area of topics you could think about. And now I tried to advance, but that kind of didn't work. Can somebody, or should I? So here's a slide problem, but not a slides problem. So Diana, I give you back the controls. Okay. I think otherwise I'm messing things up. Can you do that? Okay, so if we look at academic, basic research is a wide community. And in fact, a lot of the use cases that appear in industry appear in modified form also in academia. There is the use of a quantum computer as outlined in the presentation that you just heard for research data analysis, model identification, and measurement schedules that requires AI and optimization, just as in the last talk. But also in simulating quantum systems, as you have heard in the talk before by Peter Limmacher, very similar methods are simply applied to different problems, to those of nuclear and particle physics, to those also of theoretical chemistry, just for different chemical goals, which requires quantum simulation tools in a very wide and flexible range. And I'll come to that, what that means. And one specific thing in data analysis is the on-the-fly searching, stay on the previous slide, please, on slide 34, of unsorted data. For example, if you just have characterized the genome and you want to inform your experimental run, you better be able to search quickly. There's a second class, which is essentially research on quantum information, which is where quantum computing is from, and where it's important that there are test beds for academics to make their contributions that can eventually be very early in the chain towards marketplace. This can be on how to deal with imperfections with quantum devices. This can be in understanding heuristic quantum algorithms, so unproven quantum algorithms, but also experimental test beds. Next slide. So on the next slide, there are kind of cartoons of this. On the upper left, there is the issue of real-time data analytics, where time really matters because you're analyzing data while you take them. And with these small quantum computers that we have initially available, we will certainly not be able to search through big data, but to go through small data quickly, for example, in genome sequencing. On the lower left, what you see is a chemistry use case, such as the one that was explained by Peter Limmacher, but it's on a very academic system. It's on the complexes of hydrogen cyanide that can go from a single hydrogen cyanide molecule to long chains and complexes. And this is important because hydrogen cyanide is the molecule that essentially drives life when you go from anorganic life on a planet to organic life that can support life. And we need to understand under which conditions this happens to understand on which planets life can happen. And for this, the conditions of this reaction need to be modeled well. And for this, quantum computers can have a large input. On the right hand, there are examples of quantum computing research that requires access to quantum computers. On the upper right, there are cases from measurement entanglement and measurement bounds of information capacity, which is needed to understand quantum information a lot better. On the lower right, there is a picture of a big cryot insert which is clearly way beyond what an academic can typically have in their group, but which they need to test their developments for in a larger context. So these are examples of basic research applications of quantum computers. And on the next slide, there are a few requirements what is needed, because scientific discovery always lives by pushing equipment to its extreme. You do not find this in the user's manual. So whatever we offer to basic science needs to have deep access, it needs to be hackable, constraints should not stand in the way of using it. Specifically also trade secrets. If it's patented, it's actually okay, because what is patented is known, but sometimes they're non-patented trade secrets. The access should be very diverse. It should allow quantum information scientists who know a lot, but also users. For example, if you have a master's student from biological sciences, they should be able to use the machine without needing to learn all of its inner workings. And this needs to be merit-based. Basic research lives from breadth. So even people at small universities based on a merit-based proposal system should be able to access this, and then have some refinancing by the funding agencies of countries. I think it needs to be also be compatible with the streams of university funding. And we should keep in mind that there's not only a large community, but some of this type of research in the past has strongly influenced computing. Physicists were the first large-scale users of neural networks in the 90s. And after all, physicists have invented the World Wide Web. This needs open access to software and hardware. Thank you very much for your attention.
Thank you very much, Frank. So now we leave the topic quantum computing, and the next one is quantum sensing and metrology. The next speaker is Frank Deppe from the Walter Meisner Institute and Technical University of Munich, and he's also project coordinator of QMIX. Please go ahead.
Thank you very much for the introduction. I would like to present a use case on the application of potential applications of propagating quantum microwaves emitted from superconducting circuits. I'm trying, I've asked for control. Yeah, okay. No. Okay, I'm waiting for the slides. Here we go. The resource of quantum microwaves has been established in recent years. So typically we can now make very nice two-mode squeeze states or entangled bell pairs in the 5 to 10 gigahertz regime. And despite the low photon energies, we have found that we have very low loss superconducting waveguides to transmit them. And we don't have frequency conversion losses to other microwave platforms such as superconducting quantum computers. So in other words, quantum microwaves are the natural frequency scale in quantum illumination and quantum local area network type of applications. A little bit less obvious are quantum applications in quantum microwave communication, so I do not want to focus on that one today. The two prototypic use cases I would like to present are superconducting QLAN, so to connect two superconducting quantum computers in a way as an alternative approach to scale such devices. And the other one is quantum radar, and there the problem is to find a remote object hidden in a bright background, and this can of course also be a civil object. In a classical device for a local area network are the standard local area networks we're using every day, we're using right now, but also supercomputers are connected in such a way. And in quantum radar, the classical counterpart would be a radar device. The classical working principle of a local area network is to exchange classical information via some microwave cables. And in quantum radar, it is to exploit classical beam correlations to distinguish the object, the radiation reflected from the object from the background radiation. The quantum advantage for quantum LAN would be very similar to a scaled quantum computing chip. So it would allow one to build a kind of quantum supercomputer in some far future in the spirit of a classical supercomputer. So this would be an alternative approach to scaling. And in quantum radar, it turns out that quantum correlations are stronger than the strongest possible classical correlations. And in a realistic scenario, this would amount to up to 3 dB fundamentally better signal-to-noise ratio. This is actually an experiment we are trying to perform in QMIX on a proof-of-principle basis and also in other projects. The underlying quantum technology are always the distribution of entangled microwave beams. These can be in quantum radar and in quantum LAN applications, two-mode squeezed microwave beams, and in particular in the quantum LAN, one could also think about discrete variables, and there are also efforts going on in terms of bell pairs. The main technological challenge for the superconducting QLAN is, for example, to the cryogenics, so to connect two quantum computing fridges. This actually has been solved recently, for example, by QMIX, but also by another group in Europe. The outstanding challenge will be to achieve high remote gate fidelities to allow for fault-tolerant quantum computing between two quantum computers, of course. In quantum radar, the millikelvin source versus room temperature object and the low probing power are the problem. The current TRL is below 3, so it's still basic science, but it has a lot of potential and industry is interested. So there are activities in the EU and outside the EU. The current industry involvement is mostly supporting in terms of quantum networks, but in terms of quantum radar, we already have projects where we have full partner companies. The application examples are, I would say, pretty obvious, and we would like to build on the classical technologies, and we would like to build on know-how in superconducting quantum computing. In that sense, I would say that propagating quantum microwaves are application relevant, and we are working on that already in terms of some projects. Thank you very much for your attention.
Thank you, Frank. And our next and last speaker in this session will be Florian Schreck from the University of Amsterdam, and he's also project coordinator of IQ Clocks. Go ahead, Florian, please.
Okay, here we go. So thank you very much, and hello everyone. I'm speaking about the use cases of optical clocks. So the optical clocks are the best clocks in the world. They would go wrong by just 1 second over the lifetime of the universe. So what can, and they are 10,000 times better than the best commercial clocks. What can we do once we bring these clocks to the market? Application areas are network synchronization, navigation, sensing, and research. Here an example. Our current telecom networks and also power distribution grids are synchronized using satellite signals from GPS or Galileo. Now imagine these signals would break down, for example, because of a solar flare or spoofing. Then our networks would cease to work. We wouldn't have mobile internet or power grid synchronization that could lead to blackouts and billions of euros lost per day in the European Union alone. But we can synchronize these networks also differently. We can link these optical clocks through telecom networks, and we can place very small and cheap clocks developed by the quantum flagship project Maximal in the cell phone towers. And then if we have a solar flare, nothing special happens. Internet just is available still. And once we have these highly synchronized cell phone towers. We can use them for navigation. We can send navigation signals to, for example, self-driving cars. We can determine their position within 10 centimeter resolution, which would be, of course, very beneficial. Here another application. We can sense what's going on underground. Imagine you live in a city close to a volcano and the volcano erupts. You would like to know about this beforehand, and you can do this by placing a network of optical clocks across your country, synchronized by telecom fibers. And now, if the magma chamber fills up, the gravitational field above it would change and the clock would tick slightly differently. You can see this by comparing the clock above the magma chamber with all the other clocks. And this gives you the ability to see underground. And if we place these optical clocks on satellites, we can get better navigation, or we can use them for research, for example, infrasound gravitational wave detection or gravimetry, figuring out the gravitational field of Earth, seeing ice coverage of Earth. And here just a summary. So the benefits of these optical clocks for applications are that they can protect our networks, it can enable better navigations and different types and better sensors. And to bring this to the market, we need to improve our technology. We need to build systems that are smaller, cheaper, more robust. And we do this within the IQ Clock project. We build smaller laser systems, more compact ones. The physics package, the vacuum chamber is made smaller, electronics, time and frequency distribution. And we also need to develop, of course, these applications and services. And once we have this, we can disrupt some value chains. All this optical clock technology, like miniature laser sources, photonic chips, integrated versions of all these optical clock components are also useful for other devices like quantum computers or simulators. And the novel applications and services enabled by these clocks can have impact on telecom, power grids, terrestrial navigation, security and defense, underground exploration, research, and so forth. And to really make this work, we of course need people trained in these new skills, people who know how these optical clocks work, how to build them, how to make them better, people in the user organizations which can optimize the usage of these clocks and develop new applications. So thank you very much.
Thank you very much, Florian. And our next agenda point is the roundtable discussion, which will be moderated by Philippe Chomaz. Philippe, please take over.
Hello, everybody. So I'm Philippe Chomaz. I am from CEA. I am the scientific director of basic research in CEA. And I will be chairing this discussion. So please, can all the participants switch on their camera and mic? And then we can start the discussion. And we have also Thorsten Last looking at the question asked by the audience. And I think, Thorsten, you have already, in fact, many questions. Maybe you can ask them one by one.
Okay, my name is Thorsten Last. I am TNO, working for TNO, Netherlands Organization for Applied Scientific Research. And excuse me, I haven't heard. I heard some feedback.
I think it's somebody.
Okay.
Some noise.
There are 5 questions coming from the audience, very interesting ones. I can initially pack them into, there is 1 QKD, 2 quantum computing, and 2 more general questions. Shall I start with the QKD question because they were the starters? Okay.
Yeah, please go on.
Marina Wald had a question on perspective on space QKD. As it seems to me, as we progress with quantum communication, satellites will become more and more important, so that we'll probably need more satellites in the long term. Is there an attempt to analyze possible impacts of quantum communication on the environment, e.g. due to energy consumption or due to increased amount of satellites in the orbit?
So please, one of the QKD speakers, please.
I think it's for Paolo Villoresi.
Yes, yes. Yeah. Thank you very much. Good, very good question. What I can say is that indeed there is an expansion on the number of satellites for the different purposes that I've tried to describe. And the point is that the quantum payload, so the part that is needed for realize the quantum protocol of quantum key distribution, for instance, is expected not to play a major role in the total budget of mass energy. Instead, the optical telescope for looking at the ground or for communicating data is definitely larger and more power demanding. So in this sense, the point is actually to envisage a way in which you can exploit the quantum technology that is not a major, say, impact in the whole, say, in the whole system, in the sense that it is not a larger part and neither the more demanding. As I said, we are looking to integrate as much as possible to find solutions that are energy efficient and that could definitely go along well with the classical part.
Thank you, Paolo. Maybe we can have another question, Thorsten?
Okay, then I would move to a more general. Well, let's go to quantum computing question right away. Question to Peter Limmacher. For the provided use case of quantum computer-based optimization routines, will you provide consultancy to your customers, or will you provide a standardized solution in form of a new SAP system?
Okay, thanks. Yeah, that's an interesting question, actually. And of course, this very much depends on what kind of optimization or logistics problems or so one is looking at. If it's something monotonous, where the task is very clear and repetitive, and there is kind of a best of breed solution, then of course it would come like as an out of the box solution that one just simply can plug in and everyone can use kind of as in a quantum as a service kind of cloud solution. However, if there is some particular need from some of the customers for a very particular problem with a very well-known shape that might profit from one or another algorithm more or less, then of course also consultation would be very helpful there. And so letting the customer choose actually on what is best for him, of course, is an alternative as well. So it pretty much depends on the use case and the problem you're looking at itself.
Yeah, thank you for this answer. I think it's a very important point concerning the use of quantum technologies, because you have different ways to use it, either directly or through some company like yours. So maybe, Thorsten, we move to the next question from the audience.
Okay, I will go through the two quantum computing questions. I look for the second one. For many optimization, from Mikael Johansson, for many optimization problems, Kawa, etc., quantum annealers can provide quite mature alternative solutions. How would the quantum computing panel compare the near future potential of gate-based computers as compared to the annealers for general optimization problems?
Maybe Mark, it can be for you because you discuss optimization.
Yes, yes, it's a very interesting question. At the moment, we are quite agnostic on the method we could use to solve this kind of hard optimization problem. So we are trying to test and to challenge both of gate-based method, for example, QAOA, which can be viewed as a kind of discretization of the quantum annealing processing, adiabatic processing. So for us, both approaches are interesting, but we have more guarantees on the covariance of the methods and on the performances of an algorithm like QAOA than on the performance and on the convergence of quantum annealing in the general case. So we are investigating both approaches, but we think that QAOA is particularly interesting because he has some guarantee on his performance according to the depth of the circuit, you know.
Okay, I think Frank would like to say a few more words. Frank?
So I think in the kind of academic community, there is a whole effort in benchmarking these approaches against each other. And one result of these benchmarks is that the currently available large commercial annealers can actually be efficiently simulated classically. So they're not really providing any long-term speed up. But there can be annealers that are as powerful as gate-based, but what currently exists is not bigger than what we currently have at gate-based quantum computing. Now that can of course change by also exploring hardware paradigms such as Rydberg atoms, which may be very amenable to really powerful annealing.
Yeah, you're right. Perhaps just a word. You're right. Talking about these simulated quantum annealers, it's also a very interesting approach where we're going to benchmark to. That is simulating on conventional devices the quantum annealer.
So maybe we move to a fourth question from the audience, Thorsten.
Okay, yeah. So we have currently already 8 questions in, so it's up to you how many I should raise there. Okay, next.
Maybe we take one more from the audience, and then we wait a little. We go through some part of the discussion we would like to touch, and then we come back to the question from the audience.
Okay. Something which hasn't, well, it's an interesting, important topic which we also should raise. It's education. Oksana Mishina was asking, there was a call for new skills for a quantum engineer. Could the roundtable participants please share their experience on which specific knowledge such quantum engineer would ideally have? I think it's a very complicated question.
Yeah, so I propose maybe that one from each pillar, communication, sensing, and computing is answering. So who would like to start for the communication pillar? Maybe George, you have not yet said much.
It is indeed a very complex answer. So from our side, the quantum engineering is understood as a broader skill that needs to link with more of the classical electrical engineering, if you like, and exercise the skills towards protocols and interfaces with a classical world, if you like. But I guess that people with a quantum background can be more precise on that.
Maybe Frank, you can continue in this line. I know that you are very strongly involved. Frank Willem, you are strongly involved in education. So please.
So I think the key thing that we need to do is to teach quantum technologies to non-physicists and identify what is the subset that they actually need to know. And in quantum computing, there is kind of a real-time experiment running since IBM and later others offered online quantum programming resources where people just with a typical hacking mindset started to play with it. And I think this points in a very good direction, but we need to systematically also understand how we formalize this instead of just randomly letting it happen. And that will make it much broader. And I think reduction of the not so relevant part for quantum of quantum science is here really the key, because otherwise those people need to get 2 degrees in university if they want to use a quantum computer for biology and not just 1.
Yeah, maybe I will elaborate a little more on this issue to start a discussion from different topics we have to cover today. Because when we discuss education, we can think about educating the people, building the quantum technologies. We can think about the people also using, as you said, Frank, the quantum technologies. And we can also think about the question about the culture itself. This means that maybe just to think that maybe you can use something, you need some culture, and sometimes a new disruption of technology has not found the customers fast enough because of the cultural problem. So maybe we can touch those 3 things, the skills for developing, the skill for using, and the global cultural problem to move towards this. And maybe it's good to move to the sensing, and maybe I will ask Florian to say a few words about it, because if we think about atomic clocks and optical clocks, we know that atomic clocks are already used everywhere. And this is a kind of first quantum revolution or beginning of second quantum revolution already at play. So it's a topic for which we have already started to use it as atomic clock, and you propose to go beyond, of course, with optical clocks. So maybe, Florian, can you tell us more about what you see from the education
Yes,
of
so
everybody?
you spoke about these three different classes of education. Let's go through them. So the first one is the people who build these clocks themselves, so quantum sensors themselves. So these people need to know about atomic, molecular, and optical physics, laser systems, electronics, and all these have all these skills. And also among them, of course, quantum mechanics. Then with quantum sensors, one thing that is a bit peculiar is, of course, that you want the users to use this as a black box. It's just time comes out, or the gravitational field or something like this. So they don't necessarily have to know the quantum mechanical processes going on in these sensing devices. However, it still requires a different mindset, because these, especially optical clocks, they are 10,000 times better than the usual clocks. So you can do completely novel things. And the users need to become aware of this. So if I speak with people from the telecom industry, they don't quite know yet exactly where they will put these optical clocks once they become cheaper and more robust. Yeah, and then the third category was
the global culture, the cultural. I mean, you need also a culture, the global culture, to change in order that those technology are used by more and more people.
Yeah, I guess it's partially also just advertisement. People are not necessarily aware of what is possible. And they look, if they are aware, they look at these complicated devices in our lab and think that can never ever be put into use. But we just have to go forwards with our technology development, and in 10 or 20 years, this will become much smaller, much more robust and simpler. And so when I think that is a cultural change a bit you speak about, that it needs, the awareness needs to rise, that this will happen.
Yes, exactly. And this maybe allows me to move from this question about education to the question about at which point we are exactly in the different fields. And so you explained it very well for atomic clocks, and then optical clocks, much more precise by a factor 10 at least. But maybe we can also ask the same question for example, the communication. And this, I would like to move to the space part, and then I would like to ask Paolo to comment about where we are and what we can foresee in the next future, just to prepare the spirit about what will be possible in the future, or maybe now already. Paolo.
So we are in a situation in which the feasibility has been proved, and also the technology was pointed out, and we know we can do it. The point is that we need harnessing a very different piece of engineer and science together and make the work efficiently. So the need of demonstrators and the need of a mentality that say use these resources from the space is the things that need more addressed the most at the moment. Okay, but definitely it's not an issue of shall we, or it's just a matter of what's the best optimal next step, and the next and the next and the next.
I would like to follow up on what you said, because I was amazed last year when I read that the 40 client, you know, those kind of tools to connect we are using today to be very secure, the tokens, our 40 client was discussing and has made some alliance joint venture with ID Quantic in order to distribute quantum keys, just to add a little more on the security. And then this is a good example of the need to think in terms of a system. It is not that we will move directly to the quantum world, but already today, quantum can add in the system of communication, and this can be a big improvement. Can you comment a little more about this system view and how classical and quantum will be working together in the future for your case in communication? Just a few words.
Yeah, indeed. You are actually adding that, because it's a more reasonable things to do, in the sense that you include a new resource that is based on totally different bases, totally different principles. And in this case, from an external point of view, one hopes to be better of insecurity. Okay? So even in case one part fails, it has the other. So definitely that's the way in which it is much smoother to get in the subject and justify the investment. At the same time, it is very much needed evidence, experimental evidence on ground, like in project in the testbed and in space, that these things are actually working, that you actually have a resource to work with. So that these are both important.
I would like to continue in this line on the computing issue, the line of timescale and the vision about how classical and quantum will work together for computing. And then maybe I will ask Peter to discuss this, because you are discussing quantum chemistry. And we know that we can do quantum chemistry on classical computers. You have shown that maybe they will improve a lot quantum chemistry calculation with quantum computers. But maybe you can comment about this, Peter, how you see the timescale, when it will happen, and how do you see the cohabitation between quantum and classical?
Yes, of course. So it is really about the timescale that remains to be decided. I would see it, yeah, definitely somewhere, in the range 5 years and plus. But importantly, I think it's also, as you said, it will not be like stepping into this age, the quantum age, once of a sudden. It really will be, first of all, an augmentation to what's already here, right? So there is the conventional computations, the conventional data centers we have already now, where you can submit your calculations or to the cloud. So it is computed on several distributed machines. This will persist. And what will happen probably is that just tiny parts of your calculations will be kind of outsourced to these quantum devices, depending on the problem. Then every machine has different capabilities, pros and cons. And so it will be much more like a hand-in-hand movement where a classical computer will identify itself, oh, this is a task that a quantum computer can do much better. So let's send it to some other machine, rephrase it, formulate it a little bit so the quantum computer can understand it and will do a much faster calculation and then send the result back. I think this is definitely the first step that will come, that one chops a large problem into tiny chunks and send it out to the appropriate machines, be it a quantum computer, but also be it a GPU or then a conventional one. And from there it starts. Then once quantum computers become more powerful, then maybe they can also take larger problems and larger. And so it's slowly going to build up instead of just the quantum computer coming and replacing everything at once. I don't think that this will happen anytime soon.
So we are already at 18 minutes in the discussion. So I will take two more minutes and then I will give back the floor to Thomas in order to conclude. But in those last minutes, I would like to cover the issue about the description of the value chain. We have already touched, but maybe we can dig a little more. And I will take two examples. The first one in sensing, and we have seen the quantum radars. And we can imagine if we can detect planes, that the description can be very important, maybe in particular from the military point of view and the global equilibrium of forces. Frank, can you comment about that, this description you see, or what you think about it?
Yes, quantum radar will in generally have to operate at low power. So obviously all applications where you do not want to push a lot of power will be have a potential for disruption in that sense. And this is the example you quote, of course, the military example. But in principle, there are also civil examples. So, for example, if you want to operate in an environment where you have a lot of other microwave bands and you don't want to disturb them in a highly urban environment or in a potentially sensitive medical environment or so, then the quantum advantage of quantum radar type sensing could be relevant and disruptive.
Okay, thank you very much. And I would like to ask the very same question about the disruption for communication. And maybe, Ames, you discussed about the medical applications. How do you see the possible disruption in the use of data in medicine and the secrecy associated with those data for the future?
Well, I think it will make quite a large impact, especially because we are moving now into the age of big data, where basically a lot of hospitals are looking or gathering patients' data, and that patients' data should be accessible to all medical researchers, so they can basically run much larger trials. As I said, use maybe artificial intelligence to devise new medications and new protocols to cure those diseases. So I think it's very important that we can make sure that basically we can say this data is secure, and also with new applications, especially coming from quantum communications, I haven't talked all about. So QKD is only one part of quantum communication, but there's also some, for example, privacy preserving access to databases. So with quantum communication, we can ensure that basically certain parts of databases are accessed without the database know what was accessed. And this basically adds to the security that we can really say, okay, the hospital has your medical data, but you don't have to be afraid. It is used in developing new drugs, new therapies, but the privacy is preserved at the same time, I think, and this is very important in our age and can help the whole of society.
Okay, thank you very much. I think we have to close the discussion. Unfortunately, we have many other topics to cover, and there is a lot of questions from the audience too. The question from the audience will be distributed to the panelists, so people can get the answer. I would like just now to thank all the panelists, the 8 panelists, for this very nice discussion. And I give the floor to Thomas for the final conclusion. Thomas?
Okay, thank you very much. I think we have discussed some beneficial use cases for quantum technology. Now we have seen that the time is over, and I would like to conclude this session. Thank you to the speakers again for your interesting talks, to the organizing team, and also to the audience for your interest. I hope you enjoyed our session. Bye-bye.
Bye-bye.
Thank you.
Bye-bye.
Bye-bye.
Bye.
Thank you. Bye-bye.
Arrivederci.